Welcome to a new video. In this video we will discuss the MOSFET amplifier transfer function in the high frequency domain. We will see how we can determine the transfer function in that domain using the extra element theorem. And this theorem is developed by Professor Middlebrook from Caltech, and you see the cartoon picture of him here. And it is a very handy theorem to determine the transfer function for complicated feedback systems. So let's see how that works out in this example for our MOSFET amplifier. Of course, we will first go in the high frequency small signal model, and from there using the theorem to the transfer function. Okay, our objective is shown here. Use this extra element theorem, short EET, to determine the transfer function A, which is given by the V out over V in the Laplace domain in the high frequency region. So we have our circuit here. You see the input Vi and the output Vo. There is a load resistor. We have also the coupling capacitors C1 and C2, and also the bypass capacitor Cs. Now those capacitors will determine the low frequency region, so we will not consider that. So we assume they are short in the high frequency region. And we will also look at the transfer function symbolically. We'll also use numbers and see what the effect is of the parameters of the MOSFET on our gain, but also on our upper cutoff frequency. Okay, let's see how that works out. We will start with the model in the high frequency region of our MOSFET. This is shown here. We see here the gate node, the drain node, and also our source node. These are actually also shown here. This is the gate, that's the drain, and that's the source. Now for operation in the high frequencies, we assume that the capacitors C1, C2 and the Cs were perfectly shorted. That means this is shorted. That's why you have a short at that source. We also assume that the DC sources are also off. That means they are not active in the AC domain, so they are also effectively ground here. So that's why we have a RD going from the drain node to ground. And also the R1 and R2 are going to ground. You see that effectively also this is short. That means the RL is also in parallel with now RD and going to ground. So we have everything here. Now what do we see here? Now in the high frequency model we see the gate to source capacitor. That's shown here, and also the gate to drain capacitor. And this is an important feedback capacitor we will consider now using this extra element theorem. In addition, we have of course our Ri and a Vi here in the small signal circuit. Okay, let's now tackle this problem and go step by step. First, we will designate here our MOSFET high frequency small signal model again in the dashed red region. And our formula we know also from the previous examples using the extra element theorem was given by this expression where you have the gain is equal to gain for a specific condition where the extra element Z is infinite, so having an open circuit, and times a correction factor given by 1 plus the Nulling impedance divided by the Z divided by 1 plus the driving point impedance divided by the Z. So everything is actually again shown here. So driving point impedance is given by ZD, Nulling impedance Zn. We will determine that shortly, step by step. Our extra element we have to choose, and also our transfer function for an open extra element condition, which is then given by this expression. So we will designate here in this case, and it's actually more convenient, this feedback capacitor as our extra element. So the capacitor CGD will be our extra element, and its impedance Z will be then 1 over SCGD. This is the Laplace domain expression. Okay, step 1 is we will remove our extra element here, in this case the capacitor, and then calculate the voltage gain for that condition, which is then calculated in actually this part for the formula. So here we go. This is now the small signal model again. Now, of course, this is opened, so we will remove the CGD, and now we will determine now the voltage gain, which is then VO over VI in the Laplace domain. So that's actually shown here. So we can divide the problem actually in two parts, since we know that this part is a voltage divider, where you see the R1 and R2 in parallel with the capacitor CGS, which is also going to ground. So they are effectively actually 3 components in parallel, divided by the series combination of Ri and this parallel combination of these 3 components. And that will be then multiplied by the gain going from the VGS to the part at the output VO. So we can divide the problem in this 2 fractions or 2 parts. So VGS, which is the gate to source voltage, divided by the input, times the output divided by the gate to source voltage, which is effectively, again, output divided by the input. So you can actually see that this is now divided out. So let me do that, and this is now the definition of this gain for the Z is approaching infinity. I will designate here some shorthand notations which will be really handy in our future calculations and expressions. So Rg is now the parallel combination of R1 and R2. And I also say that Rx is now the RO, which is our output intrinsic impedance from the MOSFET. The RD and RL, so they are effectively all in parallel, so I will designate it like so. And I will now express now here the using the voltage divided rule for this part, VGS over VI, as shown here. So this is the Rg, which is R1 and R2 in parallel with this capacitor, which is our impedance here, so 1 over S CGS divided by this plus the same thing in the numerator. Okay, now we can work it out. We can say how much is that one in the expression, how much formula. You know that maybe from other complex analysis in the AC domain, which is then Rg over 1 plus the S times the product of these two. The same thing is here, and then with the Ri, I can simplify this by multiplying the numerator and denominator by 1 plus S CGS Rg. That's what I do. So I will have only Rg here. And this is now the expression. I have to, of course, multiply this by the same part. And I will now work out the parentheses here. And I will now have this expression. Now, final one, I will now divide here the denominator, the Ri and Rg out. That means this will be a 1. This will be divided by that summation. And this will be then bring up in front. So that's actually what you see here. Why do I do that? Well, I can now recognize our gain for the DC condition where the S is 0. I also know here and recognize here the time constant which will give me now the poles. So this is actually the reason for setting that in that format. The next one is about the VO and the VGS. Well, I see here the VO, which is our output voltage in the Laplace domain, is this current in the opposite sign, so minus GM VGS, times the parallel combination of these three components, which are actually given as Rx. That's actually what you see here. So minus GM VGS, everything in the Laplace domain, times Rx. That's why we have, by the way, capital letters. If I now divide left and right hand side by the VGS, I have this expression I am actually looking for. So I have now minus GM Rx. And this is now the expression I can now use with this expression I have found for the VGS over VI and multiply that and get my expression for the VO over VI. And that's now shown here. So you see here the first part times the second part, and now I have the expression I'm actually looking for. I can further simplify that. I can bring this here up in the numerator and also designate another expression which will be again handy because this Ri and Rg are actually parallel expression here because Ri and Rg divided by Ri plus Rg, meaning it is actually a parallel combination. So that's actually what I do. I will call them Rm. And then I have now this expression together, so everything is now in more compact form. So these will be, of course, brought up frequently to memorize and remember again what we actually meaning by these symbols. So we found our first expression, first part of our formula. Okay. Continue with our second step, which means disable our input source. In this case, it is a input voltage source. That means it will be shorted. And then determine now the driving point impedance ZD looking between the nodes of our extra element. So let's bring the small signal circuit again. You see the shorted input voltage. This is now wire. Since this is the voltage source, it will be a current source. Then it will be an open circuit. Okay. This open connection, I will now look inside that. And again, bring up our shorthand notations. And I will now look in that and I will determine our ZD. Now we can do that in a more convenient way if we use a test source. So I will apply a test source there. I will designate as VT and associated IT. And now the ratio VT over IT will be then using Ohm's law or ZD we are looking for. We can always do that in order to find the impedance between 2 points. Now we need to develop our equations in order to find this ratio. Let's designate again this drain node, and now we can determine how that ratio needs to be worked out. Now this current I call Ix, and this is now the current flowing in here. And if I can now set up an equation at this node D. Now I can say this node D is also the same as that node D. So I can say the following: Ix is equal to IT plus GM/VGS. That's what I can say. So this is also what I see here. And I can now call this equation number 1. I can also say that Zi is, looking actually here, because this is now shorted, this Ri will now go to ground, will be then in parallel with R1, R2, and the CGS. Well, Rm was the parallel combination of Ri and the Rg, which is the parallel combination of R1 and R2. So effectively, Rm meaning is the parallel combination of 3 resistors here. And that, again in parallel with this impedance of the CGS capacitor, is given here as the impedance Zi. Okay, now that's that. Now then we can use Ohm's law, because then we can say, hey, Ohm's law can be used here to determine the gate to source voltage expressed in our new impedance and also our IT. Because this current here will be then flowing in the complete branch here together with this Zi. So that's what we have here. And let's call this equation number 2. Now the next one is about the voltage here. That is what I will designate, which is exactly as VO, of course, on the opposite sign, but it will be helpful to make it in this polarity because the current is going in that direction, just convenience, not really required. Then I have here the Vx, which is then oriented like so. And I have now an expression, I can say again using Ohm's law, that Vx is this complete resistance Rx, which is the parallel combination of these 3 components, times the Ix, which is going here. Which is true, of course, because this is ground, and this complete thing is our Rx, and now the voltage across that is then the Rx itself times the current flowing actually from bottom to top. That's why I actually have this plus here. Otherwise, I should do minus Rx, Ix. That's the reason why I'm actually doing that. This is just for convenience. Okay, let's call this equation number 3. Next one is the Kirchhoff's voltage law, and that will be then applied on this loop here. So I can say this test voltage will see a gate to source voltage and then the Vx, and then I will make the loop complete. So Vt is VGS plus Vx. Okay, call this equation number 4. So we are almost there. We substitute now equation number 2 in equation number 1. That means the VGS will be replaced by ZIIT, this part. So that is actually what you see here. Okay, equation number, this one can be also written in the format that you have the IT outside the parentheses. So you have actually now 1 plus the GM Zi times the IT here. Okay, that's now called equation number 5. We substitute the equation number 5 in the equation number 3 where we see the Ix. So we have now this expression. So Rx times this expression, and now you have an expression that we can use later, and we designate this as 6 in this expression where you see here as 4. But we also use in that expression the expression for VGS from equation number 2. So we will substitute equation number 2 and equation number 6 into equation number 4. That's actually our final step here. So our Vt will be then ZIIT plus the Vx expression where you see actually this expression also here in equation number 6. And everything is now, that's the purpose actually for doing that, everything is now expressed in Vt, It, and the impedances and the parameters for our circuit. So there are no Ix's anymore, Vx anymore, or VGS's anymore, so they are all gone. Why do I do that? Of course, to get our ratio here in terms of the impedances and the parameters of our circuit. Now I see again the IT can be isolated here, so I can make a big parentheses. In this case, I will make this parenthesis here, and then you see here the IT, and I will now divide it out. So Vt over It will be our impedance here, and that is then our impedance we are looking for, which is our ZD. So we have found it after a couple of steps, and this is now here given in this red box. All right. So our driving point impedance is also known. That's what our step 2. Now step 3 is finding our nulling impedance. So we will null the output. We will bring up again our input voltage back, and we will again look between the nodes of our capacitor, which is our extra element CGD, and then determine the Zn. So that's similar work. So we will again open it, but now the input voltage is not shorted, so it is back in the picture. We will now make this 0. It doesn't mean that it will be grounded necessarily, but it is now at the 0 potential. That is the meaning of nulling our output node. Again, we will look at the nodes of our CGD, which is our X element. So that's still open. So we will look now in it, and that will be our Zn. And it is actually the similar process where we set a test source, Vd, and associated IT, and that will be then again the ratio where you determine now the Zn using Ohm's law. This is actually a very powerful method, so it will be really handy if you can use this also for other problems, and it will give you nice results. Okay, I will designate this node as D, but it's also, by the way, D doesn't matter where you designate that. Now, since this is a 0 volt, meaning actually this is 0 and this is ground, that means the current through that resistor RL is also 0 amps, because 0 minus 0 is 0 volts divided by a finite value will be then 0 amps. Similar for the RD, that's also 0 amps. Similar for the RO, also 0 amps. So that means 0 amps, 0 amps, 0 amps. That means the current flowing in this direction is also 0 amps. Now, if I now want to set up our KCL, Kirchhoff's current law at this node D, what can I say? Well, I can say the following. IT plus this GM VGS as the current source will be equal to 0 because there's no current here. So that is actually what I see here, and that will be then IT is then minus GM VGS. Okay, let's designate as equation number 1. I also see the following. Since this is 0 volts, then I can say the following, that the KVL is then saying VGS is equal to VT plus 0, which is then VGS is equal to VT. So that is the next expression. Now, we are almost there actually. This is much faster than the determining of the driving point impedance ZD, because IT is now minus GM VT. So this is now equation number 2. We can substitute that in equation number 1. And now we have the expression we are looking for, and this is now almost done. You only need to do VT over IT, which is then minus 1 over GM. So this 1 over that one will give you this VT over IT. So we'll again box it, in this case the pink color, and that is actually the result from third step. So we're almost done actually to substitute this formula. So we now use the formula of the extra element. We see here the formula again back in the picture. You see here the SCGD. That's actually 1 over the Z, because if you look at the expression, it is 1 over Z and 1 over Z. That's actually this SCGD. You can also write it in that format. You see the Z and also this ZD. Okay, if I now continue substituting the parameters we have found, here the A, which is actually shown here, our Zn, which is minus 1 over GM, and our ZD is this expression. So the pink part comes here, the red part comes here, and the green part comes there. Now you look at that expression, you say, well, it is quite complicated. It's true. We have to simplify this further and then see the result more clearly. So what I will do is I will bring up this SCGD up and the minus sign in front. And I also see some other things I will do later, because the ZI I have to also work out in more detail, because that will include my capacitor CGS. So that's actually there are some hidden parameters in the Laplace domain. So we have our RG, we have our Rx, and we have our Rm, which are our expressions for the resistors in parallel. But the ZI is the parallel combination of this Rm, which is the parallel combination of these 3 resistors, and the capacitor. Well, here I see a parameter, so it is dependent on the S, so I cannot leave it like that in this transfer function. So I have to work it out, and that was, of course, an important part, so we have to look at that in more detail carefully. So if I now look at this parallel combination of Rm and the 1 over SCGS, that will be then expressed like so, and I can now use that in the expression of Zi in here. So the expression of the Zd is then shown here. You see here that we have the Zi, and here also Zi multiplied by Gm, looking from this expression. Now we will work out the parentheses, so the Rx will be then multiplied by the 1 and this one, so you get this expression. Now we try to make one fraction, so you see here they are exact same in the denominator. I try to make also this Rx the same denominator by multiplying that with the same denominator as the other two. So you have actually this one, so you see the Rm divided by this 1 plus SCGS Rm, and also this GM, RM, Rx that's actually shown here. And this Rx will be multiplied by the same denominator such that we have one fraction. We can still, of course, work out this in more detail because this Rx can be multiplied by that one and Rx also with this one. And now you have an expression where you see the constant term and also the term in terms of S and also the part in the denominator. Okay, now we have the expression you're actually looking for. That will be then here substituted. So that is the ZD. We actually need to substitute here, and that's done. You see the big expression now, and now we recognize the following: 1 plus SCGSRM is here, but it's also here. So if I now multiply the numerator of this part and also this part, when I get it here, it will be also cancelled by this part here in the denominator. And this is of course a nice result. That's why I'm actually having not anymore this, this one I mean. This minus GMRX will be then multiplied by this RG, so we have here a compact expression without this part because it's cancelled out. And I have here the 1, which is multiplied by this 1 plus SCGSRM, that is shown here. And this complete big part, SCGD times this numerator here, the long numerator, is shown here in the brackets. So we have our expression as we actually wanted, and you see here there is a 0 which is on the right half plane because of this minus. And there is a second order term here we need to look in more detail and carefully. So work it out, and you see now here again the expression. Now you see here the second order term, the first order term, and a constant. Now how do we determine from here the cutoff frequency? Because the transfer function is now determined. That was actually our job, so we are done with that. But if I now want to look at it more detail, I would like to also know what is now the upper cutoff frequency for this circuit in this high frequency model. Now for that we need to look at the denominator. So this is an important part, so I will now highlight that here. And if I look at that, I can say, well, let's first designate the parameters. The parameter for the S squared and the S, we can define it as A and B. That is our constant. So the A here is the parallel, the product of these four components shown here, and this part here is completely called B. So that will be then more compact. So I can say now the following: A squared, I mean AS squared plus BS plus 1. In here I definitely have two solutions. Now I can also write down that in this format where you see the poles, so S over omega P1, which is our first pole, plus 1. This is a more convenient way also for drawing Bode plots. The other one times S omega P2 plus 1. So the omega P1 is our first pole, and there is also a second pole, omega P2. Now if I work this out, I can work out the parentheses, so I get here S over omega P1 times S over omega P2, and also this times that, so you know how to work out the parentheses, you get actually this expression. Now you can see the A should be then 1 over the product of the omega P1 and P2, and the 1 over omega P1 plus 1 over omega P2 will be then B. Now what can we do with that? Well, suppose that one of the poles is much farther from the origin, so much farther from the vertical axis on the complex plane than the other one, so it will dominate. Now we'll designate it like so. So let's say the second pole, doesn't matter which one you name it, but let's say omega P2 is much farther away than omega P1. Now that will mean the following. The one, that's by the way the dominant pole approximation, what I now am saying, and that will be then the following: 1 over the omega P1 plus the 1 over omega P2, since omega P2 is much larger, let's say 10 times or 20 times larger, then this part is quite small compared to the part here because you divide it by a larger value. That means the 1 over omega P1 plus 1 over omega P2 will be approximately 1 over omega P1. So I can replace that by 1 over omega P1. That is the purpose of doing this dominant pole approximation. So let's bring it here and then continue with that. So we can say indeed that will be then 1 over omega P1 for this part, approximated of course, and that is the B. So we recognize that because that's in front of the S. So the B will be then 1 over omega P1. Now this is of course a nice result because now I can see the B is our parameter here. So if I now invert that, I get my omega P1, which is fantastic. So my pole frequency 1 is then omega P1, which is 1 over B, which is actually shown here. So I have now the parameters in order to determine the omega P1. And that will be then shown here. So this is now boxed here in this region. The non-dominant pole, so that is not the dominating pole we have actually as designated as omega p2, can be also determined actually from the expression of A, which is 1 over omega p1 times omega p2. Because if you look at this carefully, if it is 1 over omega p1, which is actually B, so I have here actually A is equal to B over omega p2. So omega p2 is B over A. So the pole frequency 2 is then B over A. We know the B, we know the A, that's from the parameters. So now I am actually also here done with my non-dominant pole. And now we will also prove that indeed omega p1 is much larger than omega p2. That is also, by the way, a zero frequency. We have already discussed that because this is the zero frequency on the right of plane. By the way, I have designated that as plus just to mention this clearly, and this is the right of plane 0. How about the upper cutoff frequency? Well, in the dominant pole approximation, we can say, well, this is the omega p1, which is much smaller than omega p1, I mean p2, so that will dominate. So we can say the upper cutoff frequency is determined by the omega p1, and that is our cutoff frequency, the upper. There is also a little bit more complicated and more accurate result. That is this. I will not prove that, but that is given in the advanced filter circuits. So the upper cutoff frequency given by omega sub h is then 1 over that square, where you have the 1 over the squares of the poles added minus 2 over the 0 squared. Again, we will not prove it, but this is the formula you can also use. Now, okay, let's now bring everything here. It's of course important to see the numbers, so I will use some numbers here for Ri, R1, R2, etc. And I also have here the parameters for my MOSFET, RO. The GM I will here use the GM for this MOSFET as 5 millisiemens, just an example. CGD and CGS are parasitic capacitance in the high frequency domain as 2 pico and 10 picofarads. Okay, now we will calculate first the RG, parallel combination of R1, R2, 200 kilo ohms. So parallel will be then exactly 100 kilo ohms. RM is then Ri and RG, so it will be the 9.09 kilo ohms effectively. And Rx is the parallel combination of this, and RD and RL will be then approximately 792 ohms. And I have also my omega P1 from here, and now I can use this parameter B in here and then calculate the omega P1. So I will use all the parameters, values I have here. It will give me 5.474 million or mega radians per second. And the non-dominant pole omega P2 can be calculated using the formula here for the pole frequency 2. You substitute here the values and you get here 1.269 gigaradians per second. So it is indeed much larger than the pole frequency 1. So omega P2 is much larger than the omega P1, and that's our dominant pole approximation. How about the zero frequency, which is on the right half plane 0, and that is then GM over the CGD. That is exactly 2.5 gigaradians per second, again much larger than the other two frequencies. Okay, now again our approximation for our cutoff frequency, you can see that formula. Again, substitute the omega P1, omega P2 and the zero frequency, you get here 5.474 mega radians per second. But it is actually exactly as here omega P1. So our dominant pole approximation already said you can look at omega P1 and it will be your cutoff frequency. And how about then, and that of course be in the hertz, you can divide that by 2 pi, will be here 871.2 kilohertz. Our midband gain, which is in this case the DC gain, can be calculated using the expression here for the transfer. You substitute here for S0, which is our DC gain. That will be then this exactly 0, so you get here 1. This part is disappearing because you get an S here. This part is disappearing because there's an S here, so you divide by 1, so 1 over 1, and you actually have only this. And now when you substitute the GM, RX, RG, and RI, you get here for the A mid, which is our midband voltage gain, exactly minus 3.6, and which is then in dBs here 11.127 dBs. All right. Okay, let's go down to simulations. You see here the Bode plot for the gain and having a slope here going down as a low pass filter characteristics. And you see here the values we have used for this circuit. And this is our small signal model I have used in the SPI simulator in order to generate this Bode plot. You see also the values of RI, R1, R2, and the CGS, CGD. This is our voltage controlled current source. You see the GM times VGS, that's the VGS, and you see here the 5 milli because of this 5 millisiemens. And you have also the RO here, RD, and the RL. And I measure here the output, which is the VO. Okay, if I look at that again, I bring up our results from the midband voltage gain, which is in the dBs 11.127 dBs, and our upper cutoff frequency was 871.2 kilohertz. If I look at the results, the midband gain, or the DC gain actually here, is exactly as we have calculated, and upper cutoff frequency here is 874.9 kilohertz, and in this case there is a really small error. It's 3.7 kilohertz. And if you work out actually how much error this is in percentages, are actually less than 0.5%. So you can say this is a very, very nice result. What I also would like to show you here is I have prepared a spreadsheet, and I would like to show you what the effect is of changing the parameters here on the cutoff frequency. So I would like to do that. So bring up actually the SPICE simulator and also our spreadsheet, all values of the R1 up to the other capacitors, and see what the effect is on our cutoff frequency, but also on the midband gain. So let's jump to that operation. Alright, we are now here in the simulator, in the Tina TI SPICE. You see the simulation circuit I have also presented in the presentation. And you see here also on the left the values we have used in our calculations. You see the RI and also the parameter A and B. You see also here the frequencies, the pole frequencies, pole 1, pole 2, and the 0 frequency in radians per second here. And these are in hertz. And this is now the cutoff frequency we have also determined, and also our midband gain. What I would like to know is what happens if you, for example, change one of the parameters here. Now, usually if you change the capacitor, if you increase that, you expect that the upper cutoff frequency will be lower because the time constant will be larger. We can check that in Tina TI SPICE very nicely by selecting a control element. You see actually this here, so control element or control object. I click on that one. For example, if I want to change the effect of see the effect of CGS, I can click on that one. I can click on these 3 dots, and I can say let's make a list. For example, 3 values. We know that we started with 10 picofarads, so we can say let's make a little bit or maybe 2 times smaller. 5 pico, we'll do 10 pico. We also do here drastically larger, 50 pico. So we have now 3 cases, and now if you do OK, you see here an asterisk, and we will see the Bode plot now for 3 cases of the CGS. So let's do that. So we go to the analysis, AC transfer characteristics. That's how I do it. We start at 1 hertz, we stop at 1 giga, and we only show you the amplitude here, and that's what we have here. Okay, what do we see? What do we recognize? So we recognize the following. The gain is for all cases exact same. So this is, let me bring up also the label so you can see clearly what's happening. So let me make it a little bit larger so everything is visible also clearly on the video. So this is the green one we actually had before. Let me also make that blue and also make this pink so everything is a little bit better to visible. Okay, so this one dark brown one is for 5 pico for the CGS, and that is here. You see the cutoff frequency of that one is highest. The blue one is actually what we had before, and the pink one is 50 picofarads, so 5 times larger than what we had before, and that is also a lower cutoff frequency. So you see actually the cutoff frequency is going to the left, which means it is decreasing, so as expected. Okay, let's do a different one. Let's see also the effect of the parameter. So I will remove first the effect of that one. Let's also see the parameter, the GM, because that is 5 milli Siemens here, as we have determined or selected. I know that GM will directly affect our midband gain, because affecting the CGS or CGD will not affect our midband gain, but it will affect, of course, our cutoff frequencies. So I will click on that one. This is our control element, so transconductance, and I will now do here again a list. Let's say I will make it this 1 millisiemens, and I will keep the second one as 5 milli as we had it, and I will now make it also 10 milli. So I expect this for 1 milli a smaller gain, and the gain as we have it, and then here a much larger gain. Okay, again you see an asterisk here, it means it's controlled. Now we will again do the Bode plot, same thing. And now we will run this, and let's see what the effect is now. Well, this one, the green one, is our original, so let me again make that blue so we can recognize this clearly. This one is our case. Let me also make that pink so everything is visible. And I also would like to label here everything and see directly the gains for each scenario. That's actually my purpose here. So this is it. So you see here, the pink one is for the case where you have 10 millisiemens for our GM. And that is also the highest DC gain or the midband gain, which in this case 17.15. The one in blue, which is our 5 millisiemens, which is 11.127 dB as we have it. And if you look at that one, which is our 1 millisiemens as our GM, that is actually an attenuation because it is minus 2.852 dB. So you see it is indeed decreasing. But there's also another observation. While the gain is decreasing with the GM, the upper cutoff frequency actually increases. There is an inverse relationship between them. So the increasing the gain will decrease the cutoff frequency, or decreasing the gain will increase the cutoff frequency. So if I look at this pink one, which is having the 17.15 dB, for example, and if I now want to determine there, so because you see here the label for that one, if I now want to go to the cutoff frequency, I have to go 3.01 dB down. So I have to go down. I can also type this, of course, clearly by 14.138. And if I now do OK, you see here the cutoff frequency is now at 626 kilohertz. Well, we had before 871 kilohertz. So this is going down drastically. And the gain is also increased, of course. This is in this case 17 instead of 11. But that's, of course, the price we pay. If you increase your gain, you will have a lower cutoff frequency, or that means a lower bandwidth. And that's actually what I want to show you here. You can also do that, of course, in the spreadsheet by changing the value. So if I say let's make this 10 milli, so 0.01. If I type that, you see exactly also the calculation. So 17.15 as we have it also in the simulator, and also the cutoff frequency is appearing a little bit smaller than we had here. So this is 625 kilohertz, and this is now 626 kilohertz, so very close still. And this is indeed as we have it also discussed in the simulator. Alright, this is our example considering the high frequency model and high frequency gain of our MOSFET amplifier. This is, by the way, a common source amplifier. We have discussed the transfer function using the Extra Element Theorem developed by Professor Middlebrook. And we have also shown how we can determine the upper cutoff frequency using the Dominant Pole Approximation. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation, and see you next time in another video.